Hi, Joseph. How are you? We're going to go ahead and get started. If you can check out your lab for today from Canvas, okay? Now, today we are going to do a few programs. We're actually going to do 5. You can run it in your IDE, but when I demo, I will go ahead and use the virtual machine, which is the Ubuntu that we created a while back. Okay, so if you're using your virtual machine, it's important that we set up the virtual machine before we run, so that way you can give it more processor core. And also, if you want to boost up the memory, if your system allows that, you can. So I'm going to walk through that process first, and then we will write the program in Nano and use command line to run. Now, if you're using your IDE, make sure that, because I think if you're using Visual Studio or Visual Code or other IDE, just make sure that your path is linked to your system environment variable. Okay, so in this one, we are going to do pi calculation, and we are using different techniques. We are going to implement multiprocessing to be able to utilize multiple core from our processor, and we're going to write it in Python. So the first part is part A. We are going to make a pi calculator. And so as you've learned in your math courses, pi is the ratio of the circumference of any circle to the diameter of the circle. And it is an irrational number. Okay, so that means that when it displays, the decimal form can go infinitely. Sometime we would round that off, right? But what we're going to do is we're going to implement an equation to be able to calculate pi, and this is the equation that we're going to use. So to start, if you're using Ubuntu virtual machine, before you launch your virtual machine, in your virtual box, you can click machine and go to settings, or click on the settings button. And so from here, what you're going to do is you're going to click on the system tab. Now, if you're using a newer processor that supports virtual machine, of course, that's after from i5 and later, along with if you're using AMD, you gotta make sure that it's supported for the virtual environment, of course. So we would want to make sure that our system is gonna have a certain core. So you're gonna click on system, and you're gonna go to the processor tab. And here, as you can see, I gave mine 4. So if you have a quad core, you can give your virtual machine 2 core. So that way it would see it as a machine that's using dual processor. that means just 2 core in the processor. And then we can also increase the memory by going into the storage, into the system. And then after that, we're just gonna change our RAM from the motherboard, okay? So for the processor, it's important that we give it multi-core, but if you're using your IDE and you're using a processor that has multi-core, it's automatically gonna handle that. But in the virtual machine, make sure we change our settings, go to system, and edit this before you boot your virtual machine, because you cannot change it once it's booted. So you have to shut it down and then be able to modify this. So I gave mine 4 out of the 8 that I have, and I can give it less if needed. And I felt that if I give it 4, I'm able to be more flexible as I execute the program. So that is the initial setup, and you can find the steps from part A. That's going to be part number 1, number 2, and number 3. So once you set your core, and we just need about 2 gig of memory or more. If you give it 4, it's going to be slightly faster. Then you're going to click start. So then your virtual machine will boot. So make sure that we do that. Okay. So here, let me log into my virtual machine. And then you're going to go to all app. You can search for terminal, and then you will just open your terminal. So the first program, we're just going to make a synchronous program, and simply using a function that's going to allow us to calculate the value for pi. So in the terminal, we are going to use nano to be able to write the program, or if you use additional IDE in your virtual machine, that's fine too. So for this demonstration, I'm going to use nano. So I'm going to go ahead and go to nano, and I want to give my Python file a name. So pycalculator.py. So I pre-wrote this so that way it saves me time when I have the class session. But if you want to enable your line numbers, right, on your keyboard, you can press Alt-Shift and the hashtag together, and that's going to enable your line numbers for you. So as you type, it's going to add in the line number. So in the case that if you have error in nano, it's going to be able to, you can find the line that you need to be edited. Okay, so when we take a look at the program, I'm just going to use the document. It's easier to view. We have a couple import statement, and in this, we want to look at the runtime for the program. So the first one, we are going to use decimal, and we are going to import in get context. Okay, so we're going to bring in the decimal class and get context. Mainly that is just to handle how the pi values is going to be output. Then the second line for the import is going to be your time. So in Linux, we're going to use timeit. We're going to import in the default timer, and that's going to be labeled or identified as timer. We have a function called pi. So we define a function here, and we want to pass precision. And precision simply is an object that we would create to use the get context to handle the decimal precision or the float precision when we output. And in the function definition, we want to return, and here's the equation. So we want to implement the equation as follows. Now, after that, we are going to start our clock. And then we have a tuple that contains our values that we're going to pass into the function. So then values simply is the values that we're going to use. And so that way we would be able to calculate. Then for data, we're going to have the list type, and here is where you're going to use the map method. And in the map method, we're going to pass pi function. So that's one of the parameter, and then the values. Okay. Then we're going to print the data, because when it compute, it's going to give you the pi value in a very long decimal. After that, we're going to stop the timer, and we are going to find the difference from the start and the end so we can see how long it took for the program to run. So this is a fairly simple program, and we want to look at the time for a regular Python program that is synchronous. In the second part, we will write a parallel processing program, so that way we can look at the time improvement compared to a synchronous program. So once you have your program written, you would press Control X and enter to save the same name. Then once I have my program saved, then the next step is to run the program. Okay. Any question? So to execute the program in Python, we simply write Python 3 and the file name in our command line. So you are going to get the values for pi. And remember that we pass the values in the tuple. So you have 1,000, 1,500, and 2,000. So your output is going to be in a list, as you can see here. So it's going to give you the list. Okay, that's 1, that's 2, and that's the third one. So as you can see, at the end, it's going to give you the time. So on my system, I dedicated 4 core for my virtual machine to run with 2 gig of memory. And when I execute the program, as it is a regular Python synchronous program, sequentially, I have about half of a sec or 0.48 seconds for the program to run. And we would have different output as we're using different processor and different number of cores that we give it to. So to really test today's lab, we would want to have multiple core to see how the multiple core can be applied for our processes in the parallel processing program. So in this program, right, assuming that we would just have a system on my system, it would be 4 core and some dedicated RAM. Running the virtual machine, I have this as the output for time, and it's going to produce the pi values. So as you complete the program, we would then execute the program and take a screen capture. We would note the time from the output. And we would answer the question, how many pi values were computed? So you should have 3, as your values were in a tuple. We have 1,000, 1,500, and 2,000. Any question? So as you complete this program, you can see that this is one approach on how we would be able to compute your pi value, and we simply just use Python, traditional, sequential, synchronous programming. So the interpreter gives us the output, and we use timeit to measure the time that it ran. Now, in the next part, which is starting from number 10, we are going to look at how multiprocessing possibly improve the program using Python. So for the next part, which is number 10, we're going to write the next program, and it is slightly longer. And in this one, we are going to use multiprocessing module. As you learned in the lecture, we don't need to install anything. It comes with your Python package, so you don't need to add any kind of special module for this. We talked about that when we did the lecture. So I'm going to name my second file PyCal2. So in my terminal now, I would nano into pycal2.py. And I always want to use the file extension so that way it knows how to save it as a specific type of file, in this case, Python. And we can do Alt-Shift# to show the line number. So in the second program, we are going to calculate pi values again. But in this one, we are going to make it multiprocessing. So just like the last one, you have the same import statement for the decimal using the decimal module. We are going to import in the class and get context, which is the method. Then we're going to use timeit to time the program. The third line we have in the import statement is going to be multiprocessing. And for this, we are going to import in the pool class and current process method from the module. And then on the fourth line for the import, we are going to import time. So the function definition is exactly the same as the first. Nothing changed as we're using the same equation to output the pi value and have the precision. Now added to this, for the main, we're going to start the timer. But in this one now, we're going to create a pool of processes. So like this example that you find on your notes or your text, and also when in the lecture, we talked about how we would create a pool. So we would write a with pool statement, and here we are going to have 3. So you simply use 3 in the parameter. And we would say with pool, we're going to create 3 as pool. Our value is going to be exactly the same as the first exercise. We would have 1,000, 1,500, and 2,000 in the tuple. Now, different from the first program, we are going to use pool.map for the data. So this variable is going to hold the computational value for pi. And we would use the map method, but now we would link it to the pool. And the parameter stays the same with the map method, and we will want to print the data. After that, we're going to stop the clock. And we want to output. So when we print, we want to print out the time difference. So that way we would know from the time it starts and the time it ends, how long it took for us to run the parallel program. So then after that, we would call main. So if namespace is main, we would call main. So in this exercise, we implement process pool for parallel programming. And the objective of the program is to compute pi values using the same equation as the first. So by adding the pool, we can see how parallel programming can generally give you a faster time. So coming back here, after I wrote my program, I would save. So Control X, enter. Any question? Then the next step is to run it. So simply call Python 3. And we would run the second program, so that will be pycal2.py. So in general, you are going to get the same US output. We would have a list of 3 decimal, right? 1 per value, so 1,000, 1,500, and for the 2,000. Now for the parallel program here, I would see that I have 0.46. Compare that to the first exercise above. I have 0.48. So it shaved off a little bit, a tiny bit. So from a user standpoint, they might not see a huge difference, right? But we did save some time. Here. So 0.2. So as we complete that, we would take the screenshot of the output. It shows your pi value. You can scroll down, just do 1 screenshot, that's fine. And then your time. So we would say that from my case, right, my parallel time is 0.46, etc. to compute pi values. And I did see that it is a slight improvement. Not a big improvement, but a slight improvement. So in that case, you have to make a decision on whether you want to use the multiprocessing approach or parallel programming approach compared to sequential programming approach. Now, if you're only using a single core, either on the virtual machine or on the computer itself, right, you won't be able to capitalize on this. Okay, it might give you even the same or sometimes slower. So the whole point in this is to be able to implement the process. And again, if you reflect back on what we talked about when we touch on parallel programming and then going back to concurrent programming, even writing threads, you would see that here we did not really implement any kind of features or any delay, right? We didn't really utilize the object to pause and be able to start the other process concurrently. You would see that simply it would go through and access each of the value for computation. And from there, what it's going to do is going to map it based on the location. So in a distributed way, what you would have is you would have 3 processes that would compute using 3 values. So when we make the comparison, we can take a look at how much of a time improvement there. Any question? Now, if you run this in your IDE and if you have a powerful system or a powerful processor, you would see that, yes, you do have a huge improvement. I can show you that as well. Let me go to my folder. And then we have left, here's number 10. Okay. So let me run the number 7. So this is on my IDE. .92 for the sequential. And then parallel 0.76. So it's slightly different than the virtual machine, as you can see. So it does work in Tawny, or if you're using VS Code or another IDE, it should work for those two. Okay. Now on the output on my IDE, it does cut off compared to when you run it in Linux terminal. It's going to show the complete values. It just shows ... So that means it's just going to keep going for a bit. And it does give you the output for the time. So it doesn't have to be in the virtual machine in Linux terminal. You can run it in IDE. Okay, so on here on the IDE, I do see that it shaved off about 0.2 compared to on the virtual machine, it's 0.02. So that would be very based on, you know, the application. And again, I'm using a virtual machine application. So on top of that as well. Okay. All right. Any question regarding part A? So in part A, just to summarize, we did a sequential program in Python to calculate pi values, right? It's going to output a very long 3 long decimals and the time that it did to compute those decimals. Then we did parallel programming using multiprocessing module. We timed it to produce pi values using the same equation. So we would produce 3 values, and we want to check to see if there's time improvement for parallel. And in both cases, the virtual machine and the IDE, we do see some slight improvement. On the IDE end, you would see a bigger improvement compared to inside the virtual machine. And the steps are written for the VM, so. All right. So now we are going to move on to part B. In part B, we're going to work with Monte Carlo methods to calculate pi. So this is an algorithm that use random sampling instead of the static values that we see here, 1,000, 1,500, 2,000, using the equation. This is just a different way to compute pi values, but implementing random. So the randomness is deterministic, and this is the equation. M is the number of generated points of the square, and N is the total number of points. This is not an accurate example of pi computation compared to the other equation, but this is a good illustration of how pi can be computed for academic purpose. Realistically, you want to use the other equation. So we can do the same thing in this one, just like the part A. First, we are going to do a sequential program for Monte Carlo. Then we are going to use multiprocessing in the next program. So now what I'm going to do is I'm going to nano into my Monte Carlo.py program. And let's explain the code. As you saw in the description, we are going to implement random because this algorithm requires random. And for the loop, because it's using square root, we need to bring in the math module. So we're going to bring in square root from the math module. The third import statement, we are going to use timeit to measure the time, the runtime for the program. In the Monte Carlo program, we would start with the function definition. We would have the count variable initialized at 0. Then in the next part of the function is the loop. We are going to use a for range. We would say for I in range, and N is going to be the number of input. We are going to have X and Y as random. And then for our R, that's your radius, that's going to be square root, and we would have the power of x to the second plus, so y x to the second plus y to the second. And then after that, we would include the if statement. If I is less than 1, we're going to increment by 1. As it is a ratio for pi, we would return 4 times count divided by n. So start the clock here, and this is, again, the output would be an estimate. So you would have a variable that's going to hold, and here is where you call the function pi. And then we would end the clock, stop the clock. We would get the elapsed time for the runtime, and then print out the estimate for pi. And on this one, we are not going to get such a lengthy number because we didn't really control the precision like the last. So it is slightly different in that sense as well. So after you write this program, we would save by doing Control X and then enter. And after we have the program, we would run the program. So we would call on Python 3, and then the file name. And give it some time. It does take a little bit to compute. So even on the IDE, when I tested this, right, it is approximately, I want to say 30 seconds at least. So you won't have the output right away like the other ones, as it has to loop through. Okay. So definitely a little slower compared to the part A exercise. So my elapsed time this time, and I ran it earlier, it was about 35 seconds. So now it's 47 seconds. And close to 48 seconds. And then I get an estimate of my pi. 3.14134348. Okay. And you probably read or seen articles about how scientists would utilize advanced system to compute pi value, as it would be infinitely going. So it would be endless. Okay. And this is probably a good way to really test system capability as well. Okay, so when you run the Monte Carlo program for part B, the first program, just make sure that you give it time, okay? Because it does take a little while compared to the first two programs. So provide a screen capture, record your time. And unlike the first two, we're only going to compute one pi value, and it is an estimate. So on the first two programs, the function is really designed to give you 3 decimals for pi. Okay. So the purpose of this is to show you that you can implement parallel programming with multiprocessing for computation like this. Then we want to compare this to parallel programming, and that's the objective of this week, is to look at how we can use multiprocessor or a processor with multi-core for our programs. So in the next part, we would edit the Monte Carlo program, and we want to implement multiprocessing. Any question regarding B? Okay, so I'm going to come back to my Linux terminal now, and I'm going to nano into, I think I call it Monte Carlo 2. .py. Okay, so for part C, we are going to write the next program for Monte Carlo. Similar to part B, we have random import random for the first line. Now in this one, we are going to implement multiprocessing. So we're going to bring in the module and we're going to import in the pool and CPU count. So because when you test it, you want to know the number of cores that you're using, right? So when I compare 2 core compared to 4 core, how's the time difference and so on. And just like B, we would have the math module and we would import in the square root for the calculation. Then on the 4th line of import statement, we are going to bring in timeit module. And that's simply just for us to measure the runtime. And so the pi function would be the same as the first. Okay. We would have random for X and Y inside the for range. Then we would compute R, which is the square root of X squared plus Y squared. And the if statement for R is less than 1. We will return the count. Then in the main, this is where we would add in the multiprocessor pool. So first thing, we're going to start the clock. And I want to count up the number of cores that I'm using. So we would say NP is the variable, and we would use CPU count method. And recall that that comes from your multiprocessing module. Then we want to print that to show the number of cores. And then here's our n value. Then we're going to have part count. And here is where we would implement the loop for our core. So because if I'm using 4 core, right, as it is multi-core, it needs to be able to get the ratio. So that will be my partial count. Then just like what you've seen in part A, in this one, we are going to create a pool. So we would say with pool, instead of typing out the number of processes, we can just use the variable to represent the number of processes or store the value of processes, right? Because you don't know one system could be different than the next to run the program. So here we would say processes is NP. And in my case, for my virtual machine, that will be 4. And then for my count, here is where my pool map comes in. And then I would, for the first parameter for pool map, I would have PyPart, that's the function. And then part count, which is this ratio for my processor. And then my pi estimate, I would have sum of count divided by n times 1.0 times 4. And that's part of just the Monte Carlo algorithm. Stop the clock. Find the difference from start to end to give me the elapsed time. And then print out my pi value and estimate. Then lastly, we got to call main. So we say if namespace is main, call main, which is this part. Okay, so once we put the program in, we would then save, Control X enter in Linux terminal for Nano. Then we would run it with Python 2.py. Oh, I'm missing an R. So it shows that I have 2 or 4 cores. Okay. And the output. Then it takes a second or so, or 23 seconds or so, to give me the pi value. So this is your ratio. Okay, and this is your time, and this is your pi value. So if you're running 8 cores, it's going to show your cores and then the time and then the estimate for your pi. Okay. So when I look at the sequential Monte Carlo, right, when we wrote that, we kept it the same with the loop, with the full range. So for most parts, the same as far as the calculation. So I have 47.9 seconds. And when I implement parallel programming, it is 23.4 seconds. And we can look at the step up by taking that divided by the other. We would have the percentage for the step up, for the speed up. Okay. So in this algorithm, we do see that when we use process pool, there is an improvement, largely seen through the elapsed time. Now the estimate looks different, right? And if you're using a virtual machine, you can change the number of cores and see how that would be different between 2, 4, or if you have more, you can do 8, 10, etc. Okay. You would want to have at least 2 or more core for your OS. So you don't want it to deplete from your native system when you're using virtual machines. So if I have 8 core, I want to give it like half is fine. Number, my pi estimate, where shall I look? No, you would have a different number for the pi, for the estimate of pi. Okay, I'm going to tell you why. Because it's randomly generated, and so it is. So if it's using your system time as the seed for the random, you won't have the same value as me or another student. Okay? As it is not pseudo-random seed at the same spot or the same value. So everybody's system time is different. Like you and I can run it at a different time, right? And so, yes, you are supposed to get a different estimate. And that's fine. Okay. So because it's the random. Everybody okay with that? Any question? Okay. So you do have a lengthy number compared to, okay. So that's okay. So the E, that just represents like the exponent. So instead of writing a really long decimal, it shrunk it down so that way it just indicate, it's like a way to notate a really lengthy decimal value. Okay. And I can take a look at it at the end and double check. So save your screenshot. Oh, okay. Possibly, yeah, this right here. So you would have something like this, but it won't be exactly like the other. Okay, close. Maybe like 3.14, etc. afterwards, after the 3.14. Questions? Okay, so for part C, we take a screenshot for the output to show your elapsed time and the pi estimate value, and then put down your elapsed time, compare that to the previous exercise 15B. So when I look at this is 23 seconds. Okay, compared to 47 seconds. So you would compare the time for the synchronous program or sequential program to your multi-processing or your parallel program. So if it is less, then we know that we had improved time. So one of the areas that I want to hit in this lab is to look at how we can implement distributed memory. Instead of storing it in a shared location, right, for the function, we can utilize separate section for a separate process. And so in part D, we are going to create your worker pool. So similar to what you've seen in the other parallel programs, we are going to have the pool class. But in this one, it is a container for your worker processes. So that simply is a group of processes. And we would, again, use the multiprocessing module. Now, in this one, it tells you here that it has methods which allows tasks to be offloaded to the worker processes each worker has its own storage. It is not shared like threading. So this is a way that we would expand on the space and see if we're able to save time, right? But I didn't implement the time measurement on this one, but it just shows you how you can write the pool. Okay, so let me move this down a little bit to be on the same page. Okay, so back to our Linux system for demo. I would go into Nano and write my program. So let me double check. Workers. Okay, so I would do nano workers.py. And then if I use Shift-Alt hash, I would have my line numbers. So let's come back to the document so it's easier to see. In this one, you can add the time, right? Just like what you've done in the other one, so you can look at the time if you wish. But we simply have an import statement. And if you recall from the lecture and the notes, that when we create your worker pool, we want to use current process method. So from that, we have to import in process class. Unlike the others, right, we import in pool class. This one, we're going to use process class, and we are going to import in our current process method. We have data. It is a list. And we would define a function called pfun, or process function. We globalize the data. Now, in the next statement, that's simply expand your list from 1, 2 to 3, 4, 5. So we would extend that by adding in a subcontainer, which is a tuple. And we would print result in, here is where your current process comes in. And we would put the dot name that simply shows like your ID for your process. And then pass the data. In the main function, we define the second function called main, and we create an object called worker. So whenever you create a worker pool, you want to make sure that in your main function would have your object, which is, you can call it anything you want. W, right? Here we call it worker. Instantiated for the process class. And similar to what you've seen when we did the assignment, right? Your target is going to be your function that you previously defined. So pfun. And in this one, like the assignment, we would start. So that would begin the process. And when we use the join method, it holds, right? It prevents the main function from executing and finishing until the sub-process completes. So join is there. So you want to say worker start and worker join, and that worker is the object that we instantiated. And then we print data for the result in main. Lastly, if namespace is main, we call main. Okay. So this is how we can create your process pool. Or your workers. And part of your project in this class is to implement parallel programming. And this would take up a part in your project. This is an example, but of course you would implement the concept. I wanted to see if you know how to write a program that would include, that's either multi-thread or multi-process. So then once we have our program written, Control X in Linux terminal, enter to save. Then we would call on Python to run our program. So the program is nothing fancy, right? We extend 1, 2, 3 to 1, 2, 3, 4, 5. And then the result in main is going to be 1, 2. And then if you want to add in the time element, you would do it like the other programs that we've done from part A and part B. So what it gives us is our list, right? Now, if you want to print the actual process information, like the process ID, we would go back to our assignment and notes, and you can bring in OS module and be able to print out your process ID so you can see which process is which at what time, so on. So the result of this, you're going to get 2 lists. So what happens is when you look at this program, it's creating a container that stores your workers. And because we want to use separate storage for our process, we want to make sure that our process is going to have a separate storage container. So your data, the 1, 2, gets put onto the list. We have the tuple. Okay. Now notice that in this one, we didn't really use the map method. We simply pulled the data, which is here, and later on we extend it. So what it's going to do is going to add this in. Okay. And because it is separate, now when you're looking at like an array or a list, okay, what that is each of the element is sequentially stored on to memory, like what we talked about before. So let's say that if your address start with hex 0002000, then this would be the next address, and then the next element is the following address, and so on. So it would have a group of addresses in following for your container. So that means that when I'm using multi-core, each of the core is going to have each address location as each element is indicated separately, but they are grouped sequentially together. Not necessarily in the same address, but it is sequential. So it's going to go 1, 2, 3, 4, 5 next to each other. Okay. So in number 21, after you take a screenshot, it tells you here that we create a worker in which we pass your global data list, right? Which is 1, 2, 3, 4, 5. We add additional values to the list of the worker, but the original list in the main process is not modified. So your original list is 1, 2. And so when we pass this, the main is only going to have 1, 2. So for your global data, when it accesses it with the main, that's going to be 1, 2. We later extend it by adding the tuple 3, 4, 5. So when it produces, as you can see, right, it's going to give us 1, 2, 3, 4, 5. But for the main, it's going to be 1, 2. So when it stores, even though we extend it, this is going to be in a separate location as it was created as a tuple when we extend it. The output, it's going to group them together, but they are separate. Okay. Any question? So now what we're going to do after this is we see how this is done, and we're going to come back and we're going to do shared memory with multiprocessing. So as developers, you do have options on how you would design and write your program. Like I said before, we always think about our goals and objective in the program. So the purpose in using parallel programming, you want to think about why are you using parallel programming and what is it for? Or should you be using multi-threading or threads or thread pool? Should you use more resources as we would have distributed memory compared to shared memory? Right? Think about space and time and how that can be incorporated for your program performance. Okay, so any question as far as D? This is a little bit longer than most lab, but the programs are fairly short and I copy and paste the code. So unlike the others, I usually screenshot, but just to help you out. And you can run this in IDE as well, right? Doesn't have to be, I'm just using Linux. So that way, if you prefer to use Linux or terminal, you can also use Mac OS terminal. Okay. All right. So make sure we do screen capture and answer the question. Then for part E, we are going to work on shared memory. And the chapter begins with talking about shared memory from our lecture we discussed, right? Where we would have a location that will be shared for the purpose of, accessing the data in one location, but that can also cause issue. So there's disadvantage and advantages in using shared memory. So in this one, we are going to look at shared memory. And shared memory can be used for values or array. And we want to have a counter object that will be used as shared among processes. So we want to increment that counter to avoid issues. Okay. Now, this is important to note if you decide to use shared memory. It is best to avoid sharing data between processes because it will hang up. It will cause delay. And to implement this in an object-oriented program, what we can do is we can think about how we can implement interface. So message passing is preferred if you're using shared memory. That's important. And a way that we can do this is we can use MPI. Remember that a lot of our Python can revert back to C concept, or in this case, it needs to be C++ because it's object-oriented. So MPI is an interface that is very close to what you've seen in MPI C++ bindings. And this would give you the point-to-point send receives collective broadcast. So broadcast you send to everyone would receive. You can have it scattered, spread out, or gathers. So this allows us to be able to interface with the same location as multiprocess would utilize that same data location. Okay. All right. So now, if you're using Linux or terminal, we would go ahead and nano into, and it just logs me out again, our program. So I'm going to go ahead and use nano shared.py. Alt-Shift hash, or Alt-Shift 3, same. I'm going to give you line numbers. Okay, so we are going to have an import of our module, which is multiprocessing. We're going to use process class and value class. Those are the super class. Then we're going to have it sleep. So we would import time module. And as the description includes the counter, in your function here, we would pass counter there. So we would define a function. You can call it anything you want, but in this case, we call it F. We're going to have it sleep for 1 second. Recall that at the end of the chapter, or even some part at the beginning, it talks about lock. But at the end, we touch on lock, and this is going to come up in the next few chapters as well. So when a process is executing it, we would need to make sure that we implement a lock, so that way other function is not utilizing the resource or taking over. So we want to make sure that main doesn't do that. So we would use the get lock. So here we would have a statement with counter get lock, and we would increment the value. So because it talks about here where each process would increase the counter. So when we go from process 1 to process 2, we got to increment it by 1. When we go from process 2 to process 3, and so on, we would have the incrementation there. Okay. And we would print out the counter value. Then in the main function, okay, this is where we would create the counter object and instantiate for the value class. As it is in a list, we want to pass I because that will be your index, and 0 at the start. Now we are going to create your worker pool, which is going to be processes. It is a list of your workers. So This way we would have to use process, and in its parameter, again, just like the last one, your target is gonna be your function. And then your argument is gonna be your counter. And the next part is your loop, because for this, we're gonna do 30. So whatever number of processes you want, you can put that here. And they are individual process, but using the same space. So we are going to loop. So we would say for P in processes, we're going to start each one. And for P in processes, we're going to join. So that way it stops the main from executing. So the sub processes can go. Now doing it this way, it's going to loop sequentially, and it's going to loop sequentially here. Okay, but you did have a pause. Okay. So it's pretty expected that we are going to go from 1 to 30 sequentially in this case. Now, if you want to get away from this to make it sequential, so let's say I don't want to go from the first process to the 30th process. I want to go from the first process, possibly maybe process 5, process 8. Then I have to individually create the process object for each one. So just to save the coding, right, and the effort in doing that, we would just implement the loop, which is going to give us the sequential process start and join. Okay, so when you see the section, you would see, I already know the outcome because it would loop through from the beginning to the end. But if we want individual process, then we should treat the space as individual space as well, right? But this is shared. So, okay, then lastly, we just call main. All right, so now after I wrote my program, I would save it. Control X, enter, and then I run it. Okay, so like we said, as expected, I increment the counter. I go from 1 to 30. Okay. As we see that here. And then in the counter. Any question? So coming back, like what we said before, when it loops through, it's going to start all 30. Then it's going to join all 30. And then as those 30 complete, then it's going to finish main. Okay. So it doesn't really matter how many cores you really have. Your cores would just be divided up for the 30 processes. Okay, so it's going to begin all 30, join all 30. When those 30 finish, then it's going to run, it's going to execute the main. And that's the entire program. But they are all sequential as we increment one by one. It's a way that we can interface as we're sharing the same location. So it is a collective. Okay. We're going to come back to the lock idea and how to handle deadlocks and things like that later on. So we'll touch on that. And then looking at the process pool again, and also threads. So with this exercise, you can see that this one and the last one, when you're writing the shared memory with multi-processes, make sure that you implement the get lock, the counter increment as we have multiple processes, whether you're going from 1 to 5 or 1 to 500, right? We have to have those elements. And then we would have the pool of our workers. And as we are utilizing the same space, we would loop through them to start and join and making sure that they get locked. Okay. And as it finished, it would release the lock and give the resource to the next one and the next one and so on. So even when you start, when you loop through, it's still pretty sequential for the loop. So which is why we would have this question B here, for number 23, after you screenshot. The program creates a counter object which is shared among the processes. Each of the processes increases the counter with the counter get locked. So this allows us to increment, right? That's the statement. Each process must acquire a lock for itself. So when you're using shared memory and multi-processes, you should, right, always implement your lock because that lock is needed for your process. Okay. And when it finished, it's going to release the resource for the next group or the next process. Okay. So with that, look at your output. Is there any counter that's out of order? And as you can see from my output, it is from 1 through 30. Nothing is out of order, right? So we can say that as an increment, it would finish, release the lock for the next one and the next one and the next one. So doing it this way, even when we do this, it's not fully, in my opinion, it's not fully shaving off too much time because it's still reflecting back to how it would sequentially finish the process. And because we can't have 5 processes using the same resource at once, so you have to wait for the sub process 1 to finish, then get it, and then lock it for 2, release the lock, and so on. So you're still gonna have that longer in time as it would go from one to the next sequentially. Okay, so I think ideal is to use process pool with distributed memory, and that would be more for parallel programming compared to shared memory. And if you want to use shared memory, threads are probably a better choice. Any question? Okay. So that is all that we need to really do for the lab. It's pretty simple. I try to keep it where you can see the code and it's not crazy advanced, where you can implement this and you can say, oh, I can do this. I can add this component for my project. Whether whatever your objective of your program for your project would be. Sometimes some of you want to build just like a program that would interface a customer. Other times it might be for server purposes. Whatever that might be, you really have to think about like what you're trying to achieve, what kind of task is being done, and why you're using a certain approach for your algorithm. Okay. And then you can test it for the runtime. All right. So when we're done, we just simply do a shutdown. Yeah. Any questions regarding any of the exercise? Okay, so just to summarize, we did quite a few programs today for parallel processing. We did 2-pi calculator using decimal, time it, and also multiprocessing. One is sequential, one is parallel. Using the same equation, we create process pool. Then we did the Monte Carlo method for calculating pi. One is sequential and one is parallel. Okay. And in the Monte Carlo, we implemented random. So we look at the difference there. And then on the last two exercise D and E, we look at distributed memory compared to shared memory. Okay, how to write that for shared using with lock, get lock, and then your process pool. Okay, so your workers, when you're dealing with workers, you would use the process superclass. Any question? All right. So that is it for the lab. If you don't have any questions, we can wrap up here. Go ahead and put your name in the chat for attendance. I wish you have a good weekend. If you think of any questions or any concern, you can send me a message, email, and then I will see you on Tuesday for the next one. All right, let me stop recording. I'll stick around for questions.